Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to look at finding the volume of solids formed by cross-sections that are semicircles. So in our last lesson we looked at cross-sections that were squares or rectangles. Today we're going to look at semicircles. In our next video we're going to look at probably the toughest type of cross-section to deal with, the triangle. And that's just because there's couple different triangles we can have. We're going to look at the same exact diagram or the same exact two functions from our opening example from the last video. But in this case, we're going to use cross sections that are semicircles rather than, I think we use squares in our opening example from the last video. So we're going to find the volume when we take this region right here that's shaded. And we're going to look at cross sections that are raised up out of this two-dimensional plane that are semicircles. So let me kind of draw you what I'm talking about. All right, so as always, I paused the video just so I could take as many takes as I needed to drawing these semicircular cross sections. So as you can see, we're just raising these semicircles out of that plane rather than squares. The process, though, for integrating is going to be fairly similar. We're going to be trying to figure out what the volume of one of those semicircular slices would be, and then just integrating over the entire interval to find the volume of the entire solid. So to do that, we need to know what the volume of a semicircular slice would be. Again, this would be the volume of one of the slices. Well, that's going to be the area of the circle times the distance between the bases. If we think about what a cylinder's volume would be, right, because this is where this formula comes from, you take the area of the base, so big B, times the height, the distance between the bases. So again, that area would be big B. In this case, for a circle, well, that area would be pi r squared times h, or the distance between the bases. For a semicircle, the area is going to be 1/2 pi r squared. So we're going to get 1/2 pi r squared times h, but, well, actually we'll leave it as h for now. We'll change it in a second. Now, we know we're not working with r's and h's, right? We need to figure out what could I substitute in for the radius and what could I substitute in for the height. And again, the height, you could think of that as the width here, but that dimension is the height. Okay, well, let's first start with the radius. And let me draw this pink base. Let me draw it on our other graph here. Well, the radius is going to be half of that, right? Because the length of that entire rectangle would be the diameter. So we're looking for half of that to figure out the radius. Well, the entire distance would be the distance between the red and the blue curve. So in essence, we could say diameter, we'll let D represent diameter. Diameter would be 6 minus 4 times the natural log. 4 times the natural log of 3 minus x, which means the radius, or r, would be equal to 1/2 that quantity. And you can simplify that, but I just wanted to show you everything so you could see the relationship between what a radius and a diameter is. So let's come over here. I'm going to get 1/2 times pi. Times the radius squared. So I've got 1/2 6 minus 4 times the natural log of 3 minus x. And I'm squaring that entire quantity. And then I need my h, right? Well, we know that the h is the distance between those two semicircular bases, and that's just going to be our dx, right? Because these cross sections are perpendicular to the x-axis, everything in our integral is going to be in terms of x, so we're going to have dx. Well, that's the volume of one of the semicircular cross sections. We just need to throw the integral sign in front of it and integrate over the interval 0 to 2 to find the volume of the entire solid. So the volume of the whole solid would be the integral from 0 to 2. I'm not going to actually will simplify one thing inside of the brackets, but that'll be it. We get 1/2 pi inside of our brackets. We'll get 3 minus 2 times the natural log of the quantity 3 minus x. That's going to be squared, and then we'll have our dx. Again, this would be a calculator problem. You wouldn't be asked to evaluate this integral by hand. So we can just punch it in. I'd encourage you to do that. Pause the video, see what you get. It turns out that we should get 10.314 approximately. All right, so that just shows you another type of cross-section that you may be asked to use to calculate the volume of a solid. We're actually going to stop the video here. There's not a bunch of different examples you can do. For semicircles, you could be asked to have them perpendicular to the y-axis. That could be something. But then we've already talked about, how we switch up our integral and make everything in terms of y. The idea, though, would stay the same. Right? We're finding the volume of one of the cross sections, and we're integrating over the interval to find the total volume of the solid. As always, enjoy the rest of the day, and the next time we see you, we will be talking about triangular cross sections.